Hello everyone, my name is Amir Kapashev, and together with my partner AIT2509163 we will present our group assignment on the application of linear algebra in civil engineering, specifically in bridge design.
We chose this topic because bridges are one of the most visible examples in mathematics in real life. Every cable, beam, and joint is governed by equations from linear algebra. Let's begin.
Before we dive into mathematics, let's understand the main engineering problem. A bridge must carry its own weight, and that's called the dead load. Plus, also we have the weight of the cars and the people. That's our life load. And moreover, our bridge must resist wind and sometimes earthquakes. And the main question is, how do engineers know the bridge won't collapse? And the answer is very simple. It's linear algebra. And because every force, every movement, and every vibration can be modeled as a system of equations. And that's exactly what we will explore today. Let's take a simple bridge with three joints, which we will call the nodes. At each node, forces are applied downward. At node 1 and node 3, the bridge is supported. These codes are reactions. And at node 2, a track applies a downward force. And the question is, what are the internal forces in each member? So to answer this question, we will set up the equilibrium equations at every node, and that gives us a linear system. At every node, the sum of forces must equal 0. That's Newton's first law. This gives us one equation per direction per node. For our 3-node bridge, we get 3 equations with 4 unknowns, 2 reactions and 2 internal forces. We write this as a matrix equation. A times x equals b. Here, A is the coefficient matrix, x is the vector of unknowns and the forces that we want to find, and b is the vector of applied loads. This is a classic linear system. Let's make this real. Imagine a truck weighing 200 kilonewtons is parked in the middle of the bridge, and by symmetry each support carries a half, so it will be 100 kilonewton each. And by substituting this into our matrix equation and solving it by back substitution, we find that both members carry exactly 100 kilonewtons of internal force. And this tells the engineer the steel in this member must be strong enough to carry 100 kilonewtons. And without linear algebra, this calculation will be extremely difficult for a bridge with hundreds of members. So for our simple example, we solved it by hand. But in real world, with big and real bridges, like the Penang Bridge here, as you can see, it has hundreds or even thousands of nodes. And that means that the matrix A can be by 400 by 400 or even larger. So no engineer can solve this by hand. Instead, software like MATLAB, SAP 2000 or ANSYS uses methods from linear algebra, such as Gaussian elimination or LU decomposition, to solve it in milliseconds. And the mathematical structure is exactly the same. A times x equals b, and only the size changes. So to sum up, we set up the equilibrium equations at each node, wrote them as a linear system, ax equals b, and solved for the internal forces. This handles the static problem when the bridge is standing still. But what about when the bridge moves? And what happens when wind blows or traffic creates vibrations? For that, we need a more powerful tool, eigenvalues and eigenvectors. And my partner will explain the further part, and now I will hand it over to AIT2509163, who will explain this.
So now I will talk about the vector spaces. In structural engineering, every node of a bridge can move into 2 or 3 different directions, horizontally, vertically, sometimes rotationally. So we collect all these possible movements into a displacement vector u. For a bridge with the n nodes in 2D, the vector u lives in R to n, a vector space of a dimension 2n. So this is not just abstract math, it tells us exactly how many degrees of freedom the structure has. The stiffness matrix K is a key object here. It acts as a linear transformation. It maps displacement vectors to force vectors, and if you give it displacement, it tells you the resulting forces. This is exactly a definition of the linear map between vector spaces. For a single beam element, K has this form. It depends on the material's Young's model E, the cross-section area A, the length of the L. For the steel with these values, we get the stiffness of 400,000 kilotons per meter. That means that to push the joint of 1 meter, the bridge must resist with 400,000 kilonewtons. Steel is very stiff. Now the most important part, eigenvalues. When a bridge vibrates, it satisfies the equation of the motion. M times U double dot plus K times U equals 0. Here M is a mass matrix, K is a stiffness matrix we just saw. If we assume the bridge oscillationally harmonically, that is, it vibrates at a single frequency, we substitute this into the equation and get the generalized eigenvalue problem. K times V equals lambda times M, and V is the eigenvector, which shows us how bridge vibrates. It's a shape. The smallest eigenvalue gives the fundamental frequency, the most dangerous one. The most famous example of eigenvalue failure is the Tacoma Narrows Bridge in Washington, USA in 1940. The bridge had a natural torsional frequency of about 1.2 Hz. On November 7th, the wind was blowing in a way that created a vortice, swirling air patterns, also at 1.2 Hz. The frequencies matched, and this was the resonance. The bridge started twisting violently and collapsed within hours. If the engineers had computed the eigenvalues of a stiffness matrix, which was mathematically possible even in 1940, they would have seen this danger and changed the design. This disaster changed bridge engineering forever. Each eigenvalue gives us a natural frequency, and each eigenvector shows us a corresponding shape. Mode 1 is vertically bending. The bridge bounces up and down like a wave. Mode 2 is torsion. The bridge twists. Mode 3 is a higher bending pattern. In our simplified example with the 3-node bridge, we compute 3 eigenvalues. The smallest gives frequency 0.77 Hz. Engineers then check, is the wind or traffic likely to vibrate its frequency? If yes, they modify the design, add dampers, change stiffness, or increase the mass until the natural frequencies are safely away from expected execution frequencies.
In conclusion, a bridge is a physical solution to a set of linear algebra problems. We used 3 powerful tools. First, linear systems to find static forces, Ax equals B. Second, vector spaces and the stiffness of matrix to analyze the deformation F equals K times U. And the third, the eigenvalues and eigenvectors. To ensure dynamic stability, Kv equals lambda mv. Linear algebra is not just abstract mathematics. It's literally holding bridges up. Every bridge you cross, every building you enter, these structures were designed using the exact tools you are learning in this course. Thank you.